facilitates the process of recording transactions. Okay, so these transactions can be related to a tangible asset or an intangible asset. Okay, so I'll come to these terms. What is meant by a tangible asset and what is meant by a intangible asset? It can be any financial transactions. Okay, as well as this blockchain, it facilitates tracking assets in a business network. Okay, that means how a asset or say how a unit of a business is moving from one hand to another hand, or how a community is moving from one hand to another hand. Okay, so all these records can be kept in this ledger. So here we define what is an asset. So an asset can be a tangible asset, okay, or it can be an intangible asset. So a tangible asset means means which has a physical form of itself. For instance, house, car, cash, and land. And intangible asset means these are digital assets. Okay, means which may not have the physical essence, but it still carries certain value. For instance, intellectual properties, patents, copyrights, and branding. So, so basically anything of value. So in a blockchain system, anything which possesses a value can be tracked and traded. Okay, and it involves almost no risks. Okay, and it also eliminates some timing and timing costs that are involved with the conventional centralized system. For instance, the banking system. Okay, so in a banking system, you have a certain set of threats that are usually there. Okay, so in the recent past, we are seeing that in some of the banks, for instance, PNB and all such banks, okay, there have been an onset of frauds and scams that are happening. Okay, so all such scams and frauds can be done away with if a blockchain system is implemented properly. Okay, and the core of any blockchain system, as we have seen in our previous lecture, that the cryptographic primitives, that the cryptographic operations, they form the base of the security of any blockchain system. So this justifies that why cryptographic primitives, okay, or why should one study cryptography to impart the various security aspects in any conventional blockchain system. Okay, so here we see a traditional a blockchain system that exists of wherever it is. So, instance, someone requests a transaction. Okay, so this transaction can be a record. Okay, means it can be in the agricultural aspect. It can be like a selling of a tractor from one farmer to another farmer, or it can be a selling of a commodity from one businessman to another businessman. Okay, so whenever such a transaction happens, okay, means somebody requests that, okay, I want to sell this commodity. Okay, is there any buyer in the market? Okay, so somebody requests a transaction, and this transaction is basically broadcasted onto the entire P2P, that is entire peer-to-peer network. Okay, and basically in this system, the peer-to-peer network comprises, means each network node is basically a computer. Okay, which we refer to as a node, and each such node has a certain minimum computational power with it. Okay, so until and unless all the nodes validate a certain transaction, that particular transaction will not be added onto the database. Okay, only when all the nodes validate a certain transaction, okay, that transaction will be added to this blockchain system. Okay, so this chaining of these blocks or transactions, this is basically done by a cryptographic primitive. Okay, so we'll see a certain set of data structure called so we'll see the data structure of a hash-based Merkle-Damgard tree. Okay, so basically blockchain is a suite of distributed ledger technologies that can be programmed to record and track anything of value, from financial transactions to medical records and even land titles. Okay, so it is basically a ledger which gives an account of any transaction that is happening over the network. So why blockchain? Okay, why a blockchain is required? Blockchain is required due to the need for an efficient, cost-effective, and reliable and secure system, okay, for conducting and recording financial transactions. As I mentioned before, that the present day banking system has its own loopholes. Okay, there are numerous scams that are happening. Okay, hence the system at times it tends to be non-reliable, and confusions arise that whether indeed the system is secured or not. Okay, so that is where the blockchain comes into the picture. So shortcomings of the present transaction systems. First, if you perform any transaction in a cash, okay, so cash is only useful for local transactions. That means both the buyer as well as the seller needs to be at the same place. Okay, otherwise any transaction in cash is physically impossible. Okay, and you can't, and any cash transaction it happens over a relatively small amount, because you can't count cash when it goes in the order of the lakhs or crores. Second, suppose you want to perform an international business. Okay, there is usually a long time between a transaction and a settlement. Suppose you are exporting a certain good to an international country. Okay, so settling such financial transactions, okay, you perform the transaction and you need to settle your accounts. Okay, so here you have a currency change and certain other aspects. So basically it usually takes 2 to 3 days at least. Okay, again, if you have a very large business in which you are performing business over a large number of quantities of countries, there the time consumed or time taken to settle all such transactions can be large, and you may even lose track of how these transactions are settled. Third, most often you need a third party validation. So the third party over here means the central banking system, through which you will settle your transaction between a seller and a buyer. Okay, or presence of any intermediary is required. Okay, so this often leads to inefficiencies. Further, as I mentioned, there can be certain fraud, cyber attacks, and even simple mistakes, which can tremendously add to the cost of doing the business. Okay, and this may expose the identities of all the participants. Okay, so you need to remember that whenever you are performing any transactions over the network, your identity must be kept hidden. Okay, so any such threats can expose the participants in the network. Okay, so most often you would not like to expose your identity whenever you're performing a transaction over the network. Okay, and if a central system such as a bank is there, such security can be compromised. So we have a limited transparency and inconsistent information that hinders the movement of goods in the shipping industry. Okay, most often it happens in a shipping industry. So transaction volumes worldwide are growing exponentially and will surely magnify the complexities, vulnerabilities, and efficiencies. And most often this increases the cost of current transaction systems. So that's why, in place of a central banking system, most often a blockchain system can be a much more effective system. For instance, if you are keeping a land record of a certain place, means that place can be a remote village area, or it can be your that plot of a land can be within an urban area. Most often we see that the land records of certain plots of land, they are not kept properly at the land record offices. Okay, hence selling and buying of such land plots, it becomes very difficult. So if such land records could have been kept in a blockchain system, okay, then transactions of these land plots would have been much simpler in a blockchain system. Okay, so in this lecture we'll see certain aspects of cryptography. Okay, certain background of cryptography. Okay, how are they applicable to the blockchain systems? Then we'll see two major cryptographic primitives. First is hash functions. How are hash functions applicable to a blockchain system? Then we'll see digital signatures and both of their applications. Both applications of both hash functions as well as digital signatures to a blockchain system. And then we'll see some examples of cryptocurrencies. Okay, what we'll see here is basically toy examples. Okay, but you will just get a feeling that how large cryptocurrencies, for instance Bitcoin, employ such hash functions and digital signatures. Okay, so we'll see an example of a cryptocurrency in this talk. So to start with the crypto background, so we'll start with the hash functions. Okay, so basically, what are hash functions? So in in the conventional data structures and algorithms, we have seen that hash functions, these are basically means you create a bucket in which you add the keys. Okay, if a key matches with a certain record, you keep that record into that bucket. That is called a hash table. But over here in a hash function, what does a hash function do? Uh, this is the diagram of how a hash function is used in keeping a record of the transactions in a blockchain. So basically, so coming back to the aspect of hash function. So a hash function, it basically takes an arbitrary length string. Okay, that the length of that string can be anything from 0 to a very large value. Okay, but these hash functions, what do? They basically compress that string. Okay, so given an n-bit length string, the hash functions, they usually give a finite length string. Okay, so that finite length can be a 256 bit, can be a 512 bit, or it can be even be a 1024 bit. Okay, so hash functions, they take in an arbitrary length string and it gives a certain fixed n-bit length string. So conventionally, these hash functions are basically used to keep a transaction in a record. Okay, for instance, here we see that the owner of a particular record means suppose there is a seller and a buyer. So there are two identities. So two transactions would be created. So over here, the means each person or each person who is involved over here, he has his own public key. That public key is shared among all the participants in the network, and there is a private key which is usually kept secret. Okay, and this hash function is basically used to. This hash function takes in the hash of the previous block. We'll see how it is computed, and to generate this owner's signature. Okay, so this hash function is used in almost every transaction. Okay, so it keeps so basically this line is basically the signature of all the previous transactions, and it takes in the owners, that is the person who is involved in that particular transaction, his public key, and it hashes to the owner's signature. So it generates the owner's signature. Okay, so we'll see how are these hash functions implemented, or what are the different characteristics, or what are the different properties that the hash functions in a blockchain should satisfy. So what is a hash function? Coming back to the point, it takes in any string of any size as input. Okay, so that size can be anything from 0 to a very large value, but it gives a fixed size output. So for blockchain, it is usually 256 bits. So in a blockchain, we'll see that that the conventional hash function that is used, it is a sharp 256. Okay, and that this hash function should be efficiently computable. What does efficiently computable mean? Efficiently computable means that a hash function, when it takes an arbitrary size input, okay, so that size may vary from transaction to transaction. Okay, efficiently computable means after getting that input, that hash function should compute the output in polynomial time. Okay, it should not be the case that the output, that to generate the output you need to wait for a very long time. Okay, so that so this computation time should not be of exponential order. It should be in a polynomial time. Further, there are certain security properties that a hash function should satisfy. First, it should be deterministic. So what does deterministic mean? Deterministic means if I give the same input to a hash function, it should generate the same output. Okay, so if at this point of time, if I am giving an n-bit input, say all ones, okay, so the output it is generating now, okay, and if I give the same all ones input, say after 1 hour, okay, this hash function should generate the same output that it has generated now. So this means it should be deterministic. That means it should not be probabilistic. For a given input, it should always generate the same output again and again, okay, whenever that input value is being assigned. Second, collision resistance. Okay, so I will come to the details of each of this. Third is the hiding. means there is a hiding property. Then fourth, the puzzle friendly. So this puzzle friendly, this characteristic or this properties is basically applicable to hash functions that are applied to a blockchain system. This puzzle friendliness, this is not necessary for other applications of a hash function. This is specifically required for a blockchain system. And fifth, if you produce a small change in the input, okay, the output hash value, it should change randomly. Okay, means just by observing the two output values, okay, an attacker should not be able to guess what changes you have made in the input. Okay, so this is what is meant by small change in input changes its hash value. Okay, basically it should almost randomly change the hash value. So just by observing the output, one should not be able to guess what was the change in the output. Okay, so these are the certain set of the security properties that a hash function should satisfy. First, the deterministic, as I explained, no matter how many times you give a particular input to a hash function. Hello. So deterministic means no matter how many times you give a particular input, means if you repeat your input again and again to a hash output to a hash function, it should always produce the same result. So that is what the deterministic means. Okay. So what happens if this property is not present? If this property is not present, means if a hash function is not deterministic. Okay. For instance, if a hash function is probabilistic, then the output that it produces, that is the signature that it produces, okay, it becomes non-reliable. Okay, so that signature can be copied by anybody else. Okay, it can be spoofed, it can be used for malicious purposes. So that's why this deterministic property of hash function is extremely important. Okay, that means whenever you are say this hash function, it generates the owner's signature. Okay, and if this hash function instead of deterministic, if it becomes probabilistic, then for the same set of input, your signature will change. Okay, and that reduces the reliability of the entire blockchain system. Hence, a hash function should be deterministic. The second property that a hash function should satisfy is a collision resistant. So what does a collision resistant mean? It means that to a particular hash function, if two different inputs are given to a hash function, then the output of corresponding to two different outputs should not be the same. Okay, the output should be false. Okay, so this is a comparator block which takes in the output of this hash function. Okay, you give an input x to the same hash function, you give a different input y. Okay, so this comparator takes in this output of hash function, this output of hash function, and it generates. Okay, so if the result is true, that means the hash function is not collision resistant. The output should be false. Instead of true, the output should be false. That means if you change your input, the output of hash function must change. Okay, that means for a particular output, okay, there should not be two different inputs which map to that particular output. Okay, but basically the problem is that so collision resistant means nobody can find x and y such that x not equal to y and hx equal to hy. Okay, for instance, it means that if you are given the output of a hash function, okay, an attacker or anybody should not be able to find two different inputs x and y such that their outputs are same. Okay, that means it should be computationally infeasible. Okay, that means the search space to find two such inputs should be computationally infeasible. That means it should be of the exponential order. Okay, so we'll see certain instances of this. So what happens is that as I mentioned, that the hash function, it takes in strings of any size. Okay, so this search space, this sample space or the domain is a very large value. Okay, but the output is pretty small. For instance, if it is a 256-bit output, that means the output range is 2 to the power 256. That means only 2 to the power 256 values are there in this space. Okay, but the input space can be a bit length can be a bit of any length. Okay, that input can be of any length. So obviously, the domain size, that is the cardinality of set x, would be much higher as compared to the cardinality of this of the range of the function. That means if it is it is it is it is inherently possible that you can find two inputs, say x and y, which always maps to the same output. But the sample space of this y is so high, that means say say y, say any output y is a 256-bit output. That means this size is basically 2 to the power 256. That is very high. That means even if these arrows become come closer to each other, even then an attacker will not be able to find two such arrows pointing to the same output value. The probability of finding such an output is infinitesimally small. Okay, so collisions are invisible. That means collisions are computationally invisible to find, but they are not impossible. Okay, so the question now arises that are there any collisions that can be found by persons using present-day computers? For instance, the conventional hash functions that are used in the conventional blockchain system, the the hash function is a SHA-256. That means this this hash function, it takes in an input of an arbitrary length, but it always produces an output of 256 bits. Okay, so the hash output is always 256 bits. Hence, the number of possible outputs is 2 to the power 256. Okay, so if you try to perform a brute force over this entire search space, it will take you billions of years. Okay, which is not possible in the lifetime of a person. But but uh, but there is a certain property of this hash function that is called the birthday paradox, which tells you that even if you reduce the the range of the output by half, okay, that means instead of 2 to the power 256 means even if it is reduces by 2 to the power n by 2, that means if even if the search space is 2 to the power 128, the probability of finding a collision even then stays to be 99.8% or 98%. Okay, so instead of 256 2 to the power 256, you try 2 to the power 130 randomly chosen inputs. Okay, and you try finding each of the output values. So you will have a 99.8% chance probability, means 0.998 probability that the hashes of two inputs will collide. Okay, but you need to perform this many number of queries. Even performing this many number of queries is computationally invisible. Okay, so this is due to the birthday paradox property. Okay, which tells you that suppose if you have n different possibilities of an event happening, then you need square root of n random items for them to have a 50% chance of a collision. That means to identify that whether the two events are the same or not, you need to perform square root of n number of random items. So this works no matter what h is. Okay, it's irrespective of what is your hash function. Okay, this birthday paradox eventually works, but as the sample size, that is it is 2 to the power 130. Okay, it takes a very long time. Okay, it takes a very long time. So that is basically computationally impossible for any attacker in the present day world. Okay, so that's why that's why the range is kept to 128 bits. Sorry, 256 bits. So is there a faster way to find collisions? Okay, so most recently there have been even faster way, which are improvements over this birthday paradox. Okay, that find collisions for these hash functions. Okay, so but so due to this, due to the property of these hash functions that you can have a 99.998 probability of finding a collision. So that's why no hash function till date has been proven to be collision free. Okay, so for cryptographically strong hash function, if we know that the hash values of two inputs are the same, then we can safely assume that those two inputs are the same. That means if h of x equals h of y, then we can safely assume that x equal to y. Okay, so even though it is not the case, but we can safely assume because an attacker, it is computationally impossible for an attacker to find a collision. Okay, so to recognize a large file we saw earlier, okay, we just remember its hash. Okay, so what happens is that that in blockchain systems, whenever you store large files, okay, so you often store the hash of such files. Means whenever you are say consider, means if you want to compare two large files, okay, if you want to compare the text of two large files, what is often done is that any such large file is often hashed, okay, and you match the hash value of the text of those two values, okay. And so basically, a large file, say a video file, it can be in of the order of the GBs, but its hash value would be a 256 bit. So it is much more convenient to compare the hash of large files rather than to compare the two large files. Okay, so it is useful because the hash is often very small. The third property, so the first property that we saw was the deterministic, that the hash function should be deterministic. The second property that we saw, that it should be collision resistant. The third property is that the hash function should have pre-image resistance. That means an attacker, after having observed the hash output, okay, he should not be able to compute the input. That means he should not be able to invert this hash function. Okay, so given h of x, it is impossible to find a value x. Okay, but if the sample space of the input is small, it is usually possible. Okay, for instance, if you are asked to toss a coin, okay, coin tossing can have two outputs. Either it would lead to a head, or either it would lead to a tail. Okay, for head input, you give this head input to the hash function. If you get a tail, you give this tail input to the hash function and you record the corresponding output. Okay, so as the sample space is very small in this case, so just by observing the respective outputs, you can identify what was the input of the hash function. Okay, so this pre-image resistance is only guaranteed only when the input sample space is very large. It is of the order of exponential. Okay, that's why the input size of the hash function is kept at any arbitrary length. It can have any large value. Okay, so the experiment should not have a small sample space. So x should be chosen from a set of values which is large, and it must be spread out. Okay, why it must be spread out, that I will come to you. I come to in a few minutes. Okay, so x should be chosen from a set of values which is large, and it must be spread out. So for an adversary, it is not possible to try all values of x or only few but high probable values of x. Okay, so an adversary should not be able to attempt all possible values of x. Okay, and in another case, if there are certain values of x which are highly probable, okay, he should not be able to iterate it over all such large probability values of x. Okay, so these are the certain requirements to ensure that the pre-image resistance property of a hash function. Okay, so hiding this pre-image resistance, this is often referred to as this pre-image resistance is also referred to as the hiding property. So what happens over here is that most often, if this input, this x that you provide to this hash function, if this input is very small, then what do? Most often what you do is that to this small sample size input, you append another parameter, okay, which belongs to a probability distribution that has a high mean entropy. High mean entropy means that probability the probability distribution is evenly spread out and is largely spread out. For instance, if you consider a 2 to the power 256 bit input, 256 bit input, the sample size would be of the order of 2 to the power 256. So 2 to the power 256 is a very high sample size. Okay, so uh, so what happens in that case is that the probability of hitting one sample in that case is basically 1 by 2 to the power 256. Okay, so when you compute this 1 by 2 to the power 256, that is a very infinitesimally small value. So that is called choosing from a probability distribution with a very high gender entropy. That means probability of selecting a particular value is very small. Okay, that means it is almost close to a random. So a high mean entropy means that the distribution is very spread out, so that no particular value is chosen with more than a negligible probability. Okay, that means you cannot guess. Okay, which is the next value that will be chosen. Okay, because when you try to compute the probability of choosing a particular value, that probability value will be very small. Okay, hence an attacker cannot predict. Okay, means even if he observes that okay, these are the n samples that have been chosen, he cannot predict based on these n samples. Okay, what would be the next sample that would be chosen? So that is the importance of a high mean entropy distribution. So whenever you have a small sample size, what do? You append a value, a data value, which has a very high mean entropy. So for a hash function, any particular string R is chosen with a probability such as 1 by 2 to the power 256, which is a very small value in this case. So application of a hiding property. So here we see what are the certain applications of this hiding property of a hash function. So one such property is the commitment. Okay. So what happens in this? So we'll see this example. Say suppose you have a particular value, okay, and you put that value in an envelope and seal it. Okay, and you keep it on the table for the general public to see later. Okay, what value had you kept? Okay, so at that point of time, okay, nobody knows other than you what is the value that has been kept in an envelope. Okay, so whenever you are putting a value in that envelope, this is called a commitment. Okay, so in our future set of lectures, we'll see what is meant by a commitment of a transaction. Okay, so once a transaction has been performed, okay, it is kept in an envelope. Okay, and at a certain later point of time, that envelope is opened and that value is seen. So commit to a value now, but reveal that value at a later point of time. So how is this done using a hash function? We'll see it now. So what you do is that this is the commit function, and the value that you want to seal this is the message, that is the original message. Okay, so you seal this message using a glue. Okay, so you put a glue on that envelope. Okay, and you put that envelope on the table. Okay, so that envelope is called the COM. Okay, so anybody, just by observing that envelope, he doesn't know what is there inside. Okay, so what is there is in the inside of the envelope, that is the message, and by applying a glue, that is the key. Okay, you have produced that envelope. So that envelope is basically this COM. Okay, so now at a later point of time, what do? You get that envelope. Okay, you again apply that glue. Here applying the key means you are breaking that glue to see what is the message. Okay, so if somebody else claims a message, okay, that message and this message is verified to see whether there is a match or not. Okay, so this is the convention over here. To seal a message in envelope, you perform this commit function. Okay, so you perform this commit function, and then you publish COM. That means you are putting that envelope on the table. Okay, and you seal that envelope using this key. To open the envelope, you publish the key. Okay, so what glue was used? You open that envelope, and anybody can use this verify to check the validity. Okay, what was there inside? Anybody can verify at a later point of time. Okay, so this scheme, so this commitment scheme, it comprises of two algorithms. Okay, that is sealing an envelope and then opening an envelope. Okay, so this is done by the commit function. So this commit function takes in the message, that is the value that you have kept secret within that envelope, and a secret random value called the nonce or the key. Okay, that nonce means number used once. Okay, so you cannot repeat the same glue or the same key again to seal that envelope. So you use that secret random value to seal that envelope, and you put that envelope on the table. That means you return that commitment or com. Okay, so when that, so this verify function, what it does, it takes a commitment. Okay, that means the envelope, the nonce, that is, it tries to deglue that envelope and the message as input. Okay, so returns true. So this verify function, it returns true if the message that it was given to it, it checks that whether this message was indeed there in the envelope. It deglues it and checks that whether that message was indeed there or not. Okay, so it returns true if the if both this if both the envelopes seem to be the same, means a message is again given, it is again deglued, and then the two envelopes are compared. And if this comparison is the same, then it returns true. Otherwise, it returns a false. So it needs two security properties to keep these two characteristics. That means it needs two security properties to define these two algorithms. First is the hiding property. That means given the envelope, that is the com, it is invisible to find what value was kept in that envelope. That is, it is invisible to find what is the message. And second is the binding. Binding means once I have put a value in an envelope at this point of time, okay, at a later point of time, I should not be able to claim that no, I had not kept that value. I have kept, say I have kept, yeah, at this point of time, I have kept, say, a 5 rupees note, say a 10 rupees note in an envelope and sealed it. Okay. At a later point of time, I should not be able to claim that no, I had not kept 10 rupees. I had kept 20 rupees. Okay. Where did the other 10 rupees go? So this is called the binding example. That means it is invisible to find two message pairs, that message, that means the 10 rupees note and the glue, and a 20 rupees note and the glue, such that when these two notes are different, okay, the envelope should seem to be the same. Okay, so this commit should give you the same output for two different messages. Okay, this should not happen. Okay, you should not be able to find two different message values for which this commit function, it gives you the same output. So this is called the binding function. So there are certain rules for this commitment scheme. So every time you commit to a value, it is important that you choose a new random value over nonce. That means whenever you choose this secret nonce, as I said, that when you are setting that envelope, or that means when you are performing this, when you are computing this commit function, okay, this secret value, this nonce, you should change on every query. Okay, so it is important that you choose a new random value nonce every time. So the security properties, first, as I said, given com, that means given the envelope, someone looking at the envelope cannot figure out what was the message. The binding property, it ensures that when you commit to what is in the envelope, you cannot change your mind later. Okay, that means if I have put a 10 rupees note now, in later future, okay, I should not be able to claim that no, I had not kept 10 rupees, then I had kept 20 rupees. Okay, this should not happen. So this is called the binding property. Okay, so this is what it says, that once you have committed a message in an envelope, okay, for a different message, this verify should not return you a true. Okay, you should not be able to find two different messages for which the verify gives you a true output. So using a cryptographic hash function, okay, so what do you do? So this commit function, that means you are sealing this envelope. This is being done by a hash function. So basically, this message that you want to produce a hash, this message would be of a finite size. Okay, so So most often this is of a finite size, and hence as the sample space of this message is very small, you append to it a nonce, which is a very large key value. Okay, so a nonce is a random 256 bit value. So as it is a random 256 value, that means the sample space for nonce is 2 to the power 256. That means it is a pretty it is pretty hard for any attacker to guess what was the nonce that was used over here. Hence, you compute. Hence, the entire sample space is pretty much large. Now you have an X of a very large size. Okay, hence this pre-image resistance is restored. The property of hiding or the pre-image resistance is restored in this case. Then you have the verified. Okay, so so again a com is given. Okay, and this verified, it checks that whether this com is indeed equal to the hash function or not. Okay, that means you just compare two hashes basically over here. So the security property hiding, it means that given the hash of a nonce appended with a message, it is invisible to find the message. Okay, even though the message space is very small. Okay, you are to the message. Okay, you are appending a very large sample space. Okay, nonce has a 256 bit value. That means its sample space is 2 to the power 256. Hence, an attacker cannot guess a particular value with a significant probability. Okay, that means even if this output space is smaller, okay, an attacker cannot guess what was the input because the sample space is pretty high for the input. So this confirms the hiding property of the hash function. Then you have the binding. So binding means for this hash function, when you use the same hash function for two different messages, okay, even when you append those two messages with a large 256 bit value, the output of the hash should not be the same for two different messages. Okay, you should not arrive for two different messages. The hash should not produce the same output. So this is called the collision resistant property. The fourth property that the hash function should satisfy is the puzzle friendliness. So this is quite related to the hiding property. So a hash function is puzzle friendly if for every possible n bit value output, if k is chosen from a distribution with high mean entropy, then it is invisible to find x such that h of k given x equals y in time significantly less than 2 to the power n. So what does puzzle friendly means? That means a hash should facilitate a hash function should increase the hardness of the puzzle. For instance, the problem here is that to an attacker, he is given the output sample space. That means from what sample space this output is chosen. Okay, even though the sample space is small, okay, this x is the input to this hash function which an attacker wants to obtain. But as this small input sample space x is appended with an input from a high mean entropy distribution. As I said, what is meant by a high mean entropy? High mean entropy distribution means probability of guessing a particular input being chosen is negligibly small. So that means this entire sample space becomes very large. That means even after an attacker, even if he is given this sample space, the output sample space and a particular output value, he should not be able to guess what was this value of x. Okay, so he should not be able to guess this value with a time less than 2 to the power n. 2 to the power n means it is an exponential time. So it should take an attacker an exponential amount of time to guess this value of x. So this is called the puzzle-friendly property of the hash function. So a search puzzle. So basically, a search puzzle in a blockchain system, it comprises a hash function which satisfies all the prior properties that we discussed. So it comprises a hash function. It comprises a value ID or a puzzle ID. Okay, so this k is basically a puzzle ID which is chosen from a very high mean entropy distribution and a target set y. Okay, so this y is chosen from a sample space. So that sample space is given. So that is called the target set. So a search puzzle. So I repeat, a search puzzle, it comprises of a hash function. a value ID. Okay, this ID is chosen from a high mean entropy distribution and the output sample space, that is the Y, that is the target set. So a solution to this puzzle, that means the attacker who tries to solve this puzzle, what does he want to do? He wants to he wants to find this value x, the value of this x. Okay, so a solution to this puzzle is a value x such that when an attacker is given an output sample space, even though this output, even if the output sample space is small, an attacker should not be able to get the value of x. Okay, so this is called the puzzle-friendly character. Okay, so this is the search puzzle, and the job of an attacker is to find this value x given this y. Okay, and this ID is chosen from a high mean entropy distribution. That means the sample space of this ID is so vast that the probability of choosing any particular value is infinitesimally small. So so this is the basic properties of a search puzzle that is used in a hash function that is employed in a conventional blockchain system. Next property, as I mentioned, that any small change in the input should change the hash output drastically. Okay, so this property, it ensures the immutability property of blockchain. That means any record that is being put in a blockchain, it cannot be tampered with. Okay, so this is referred to as the immutability property of the blockchain. So in this, say suppose this is the input to a hash function. So in this is the string that is given to a hash function. So in both these inputs we see that at the first letter, this is an uppercase T and this is a lowercase t. Okay, so even if the character has been changed from uppercase to lowercase, the corresponding hashed output, it seems to be a random. Okay, it is basically a pseudo-random string. That means after having guessed, even if an attacker is given these two hash values, okay, he should not be able to distinguish that the corresponding input string has only this change. Okay, so this information he should not be able to recover. Only then that hash function can be referred to as a cryptographically strong hash function. Okay, so here we come to the hash function that is used in the conventional blockchain system, that is called the SHA-256. It basically uses the compression function C. Okay, so what does a C take in? A C takes in a 768-bit input and it gives out a 256-bit output. So it basically compresses the data. Okay, so it takes in a 768-bit input and it produces a 256-bit output. So C is a fixed length and a collision resistant function. Okay, so basically the security of the SHA-256 it basically relies on the security properties of this function C. Okay, so this C is a fixed length and it is collision resistant. Okay, so this construction is called the Merkle-Damgard construction. Okay, so as I informed before, that this SHA, it can take an arbitrary length bit string. Okay, so what happens is that the input to that hash function, it is being partitioned into 512 bits blocks. Okay, so this message is split. The entire message is split into 512-bit block. So in the first iteration of C, this 512-bit block is given as the input, and then an IV of 256-bit is given. Okay, so these two add up to 768 bits. Okay, so this IV is the initialization vector. Okay, it can be any random vector, and even this can be known to an attacker. Okay, so this is publicly known. Initialization vector is publicly known. So this 768-bit input is given, and this C function, it generates a 256-bit output again. So this 256 output, it is then given to the next compression function along with the next message block. So this is also 512 bits. Okay, so this entire message block is split into 512 bits, but if this message block is not a multiple of 512 bits, then zeros are padded at the end of the last block. Okay, So this is a chaining system, and this entire construction. So the last C function, okay. So this continues until unless this message ends. Okay. So this last C function, it produces the final hash output of 256 bits. So this entire construction is called as the Merkle-Dampert transformation. So this construction is called the Merkle-Dampert construction. Okay, so this so just by iterating this compression function C, this entire hash function can take in an arbitrary length string. So now we come to the next topic called the hash pointers and data structures. Okay, how in a blockchain system, okay, how the records are kept. You see in this, what are the data structures, or what are the data structures that are used to save a record. So whenever a data or a transaction is being kept in a blockchain system, what is being done is that along with the data, the hash of the data is also stored. Why is it so? It is because that whenever a data, if this data is tampered at any point of time, okay, because this record is publicly available, okay, so if somebody tampers with this data, then the corrupted data will not match with the hash, okay, because this hash was with respect to the uncorrupted data. Okay, so this ensures the tamper-proof security of this record. Okay, and what does a hash pointer means? A hash pointer means the pointer points to the data as well as the hash of this data. So a hash pointer is a pointer to where the data is stored together with the cryptographic hash of the value. Okay, so the data is stored along with this cryptographic hash value. Okay, so this hash pointer, it basically points to the location where the data and its cryptographic hash is being stored at some fixed point of time. So a hash pointer also gives you a way to verify that the information has not changed. For instance, if you want to go to a record, what do? You go to that pointer value, okay, and from the pointer value you go to the data, and at the same location as the data along with its hash value is there, what you can do is that you can pass the data to that through that hash function, and you can compare the output of that hash function with the hash of this hash from this location. So if the two hashes are the same, then you conclude that the data has not been tampered with. But if the two hash values, that is the hash that is being stored along with the data and the hash that you just computed, if those two hash values differ, that means you can conclude that the data has been corrupted. So a hash pointer, it facilitates at whether the information or the record that we have stored here, whether it has been changed or not. So we can use this pointer-based data structure, this hash pointer-based data structure. You can use in any data structure, be it a linked list or be it a binary search tree. Okay, you can use hash pointers to be used. Okay, so this is a blockchain. So this is how a chain of blocks is being stored. Okay, so I'm not going into this is just showing the crux of the system. So this is a linked list representation wherein this hash pointer, it points to the first record, okay, and at this location along with the data, that is the record, okay, you keep a hash value of the data as well. Okay, then it points to the previous record. Okay, so whenever you add a new record to the system, it is added over here, and then this head pointer, this is the head hash pointer, it points to that record. Okay, and whenever you create that record, it should point to the next latest data. Okay, so whenever you are storing a data, you are storing the data along with its hash. Okay, so whereas in a regular linked list, you have a series of blocks. Each block has a data as well as a pointer to the previous block in the list. In a blockchain, the previous block pointer will be replaced with a hash pointer. Okay, so instead of a pointer, you now have a hash pointer. Okay, because that pointer is pointing both to the data as well as its hash. Okay, and they are kept at the same location. So each block of data, what does it tell? It not only tells us where the value of the previous block was. Okay, so from this data block, okay, once you have read this data block, you also get the location of the previous data block. it tells you the value of the previous block. It also contains a digest of that value that allows us to verify that the value has not changed. Okay, so this digest means the hash of that data. Okay, a digest is nothing but a hash of the data. So you can pass this data or the record through a hash through the same hash function to get the corresponding hash output, and then you compare the hash value that is stored with the data along with and the hash output that you obtain from the hash function. So through this you can generate a tamper evident. So this log is a tamper evident log. Okay, so it gives you an idea, an evidence that the log has not been tampered with. So what happens over here? So if an adversary, say suppose an adversary, he tries to modify a certain record in this blockchain. Okay? So if he modifies the corresponding record over here, okay, in this set, he has to modify the corresponding hash as well. Okay, so along with this hash and the pointer, okay. For a malicious user, if he changes this data, he needs to change its corresponding hash as well, so as to escape the detection. Okay, so whenever he changes this hash, then it changes the hash of this entire record, okay, which is being stored over here in the previous block. That means if an attacker wants to change a particular data in a certain record, okay, he needs to change he needs to change the data in its subsequent records as well. And at the end, okay, over here, if means when he has changed the data in the last record, okay, but when this data has been changed, the hash of this data will not match with the hash of the pointer. Okay, so over here the tamper means it will be detected that this record has been tampered with. Okay, so if an adversary modifies data anywhere in the blockchain, it will result in the hash pointer in the following block being incorrect. Okay, a hash pointer would give you an incorrect value. So if we store the head of the list, then the adversary modifies all of the pointers to be consistent with the modified data. Okay, so if he changes any data, he has to change the hash pointer of all the blocks subsequent to it, so as to remain consistent. But at the end, he doesn't know what is the header pointer. Okay, so when he changes the hash value over here, that means the hash value of this entire block, it then changes, and then it will not match with the hash value with the header pointer. Okay, and hence this tampering would be detected in this case. Okay, so this blockchain construction is similar to the Merkle-Dampert construction. Okay, so as I said, the construction of the hash function, so that was the Merkle-Dampert construction. So this blockchain construction is also a Merkle-Dampert construction because it is of a linked list structure. Okay, so the block that is at the beginning of this linked list, this is called the genesis block. That means this is the most recent block. So this is how the transactions are stored across in the blockchain. So here you have a series of transactions. So basically a block, it contains the record of numerous transactions. Okay, so here you have 4 transactions: tx0, tx1, tx2, and tx3. Okay, so for each of the transactions you have the corresponding hash values: hash0, hash1, hash2, and hash3. Okay, and then both and the hashes of 2 subsequent blocks, they are being kept together, and the corresponding hashes values are then computed. Okay, so this is how a tree kind of a structure is being employed. Okay, and the root of this tree is being stored in this block 11. So a block comprises of the previous hash, that is the hash of the previous block, the timestamp, that means at which time a certain block has been created, the root which points to the tree. Okay, that means a pointer to the root. Okay, so once that means means once a user is given this root value, he can traverse this binary tree to go to a particular transaction. Okay, and then a nonce. Okay, so this nonce is used to compute that hash function. As I mentioned, that a nonce means this nonce is very important to restore that cryptographic property of the hash function. So you have a block 10, block 10, 11, and block 12. Okay, so these are the blocks. Okay, so this is the structure of a transaction in a blockchain. So this is called the Markov tree. So this is how this data is being stored in a blockchain. So you have this binary search tree. Okay, so from the TX root, okay, you can come to this node. So this node comprises of the hash pointer, okay, two hash pointers. Okay, so to locate a data, you can traverse through this respective path. Okay, so in a Merkle tree, the data blocks are grouped in pairs, and the hash of each of these blocks is stored in a parent node. Okay, so you compute the hash, and then computing the hash takes you to the next level block. So the parent nodes are in turn grouped in pairs, and their hashes are stored up one level up the tree. This continues all the way up the tree until we reach the root node. Okay, so the hash of this value is points to the next node over here, to the child node over here. So to identify that whether a data or whether a record indeed exists in a blockchain or not, that is called the proof of membership. That means whether a data is in the blockchain or not. Okay, to identify that whether a data is in a record or not, called the proof of membership. So to prove a data block, that whether a data block exists in a record or not, you need to perform order of log n number of searches. Okay, so these are the log n. So if your tree size is of n, as it is a binary search tree, to identify a data, you need to have, okay, you are computing a log n time complexity to get to that data. That means whether a data is there or not. So you can even identify that whether a data is there or not. Okay, so over here, even though so I'm saying that it's not a binary search tree. This is a binary tree. Okay, so you can even identify. You can also have a proof of non-membership over here. Okay, so if there are n nodes in a tree, you need order of log n items to be searched through. Okay, so that means even if this Merkle tree contains a large number of nodes, we can still prove membership in a relatively small time. So verification thus runs in time and space that is logarithmic in the number of nodes in the tree. Okay, so both time and space is of the order of space means search space over here. So time and search space is logarithmic. Okay, so this is a Merkle tree to store the transactions over here to pinpoint where your data is located. So you can also have a non-membership proof. Okay, so to identify whether to pinpoint or to say that the data does not exist in a blockchain, what do? You do a sorted Merkle tree. What that means, what you do over here is that the diagram is not here. What you can do is that you can sort this data. Okay, so you can sort this data in an ascending order or in a descending order. Okay, so you arrange this corresponding nodes as well. Okay, so what you do is that whenever you intend to find a data, you can go to the data previous to it. Okay, so suppose this data is of a smaller value compared to this. Okay, then you go to the next data. Okay, that data can have a higher value than this. Okay, so if two neighboring nodes has a value such that the left node has a smaller value compared to the value that you are searching for, and the next subsequent node has a higher value in comparison to the data value that you are searching for, and if those two nodes are neighbors, that means both are the child nodes of the same parent node, then you identify that this data is not there. So this is called the proof of non-membership. That is called the non-membership proof. Okay, so to have the non-membership proof, you do a sorted Merkle tree. Okay, where you take the blocks in the bottom and you sort them using an ordering function. So this ordering function can be either an alphabetical, lexicographical, or a numerical order. So I gave the example with a numerical order in which you sort the data blocks in a ascending or a descending order. So in the proof of name membership, you show a path to the item that is just before the item in the question, and then you show the path to the item that is just after, where it would be. And if both these items are the child nodes of the same parent node, then the non-membership is being established. So if these two items are consecutive in the tree, then it serves a proof that the item in the question is not included. That means that item is not there in the tree. So more generally, we can use hash pointers in any pointer-based data structure that has no cycles. Okay, as you first need to identify the root of the tree. Okay, so basically this pointer-based data structures you can this hash pointer you can use for any tree-based data structures. Okay, or any graph-based data structure, but you need to be sure that that graph should not have any cycles. For instance, you can apply this hash pointers to any directed acyclic graphs, that is DAGs. So you start at the root node and then approach towards the leaf to pinpoint that data that whether that data exists in the record or not. So the next cryptographic crypto primitive that we come across is the digital signatures. In the digital signature, what you do is that you take a document, okay, and the system should guarantee is that the person who generates that document only that person can sign that document. Okay, the person who has signed this document, okay, the person who has generated this document, only that person can sign. But this signature can be verified by any other person in the system. So what we want from the signatures, only you can sign, but everybody else can verify. Okay, and the signature is tied to a particular document. That means if you change the document, your corresponding signature, your corresponding digital signature should also change. Okay, otherwise if this property is not there, then your signature can be copied from one document and it can be pasted to another document. Okay, so a signature is tied to a particular document. That means when you change your document, that means when you change your message, your signature also change, so that it cannot be cut and pasted into another document. So how can we build this in a digital form using cryptography? So what do you do to create a digital signature? First, you call a function called the generate keys. So in the generate keys function, you give the parameter that what is the key size, what is the size of the key that you what is the size of the key that you want to generate. So this generate keys, it creates a pair of keys. The first is the secret key. That secret key means this key is secret to the owner only. Okay, nobody else other than the owner knows the secret key. Okay, and the other component is the public key that is known to everybody else in the system. So this is a key pair wherein the first is a secret key that is known only to the owner, and then we have a public key that is known to everybody else in the system. So this function, it takes in the key size and generates a key pair. So here SK is the secret key and PK is the public key. So the secret key is used to sign the document, okay, and the public key is used to verify that document, okay, to verify that signature. So this secret key is kept privately so that only the owner can sign on that document that is in possession with him. So it is kept privately and it is used to sign the messages. So how do you sign the message? So this message is a document which you want to sign, and you sign it with SK, that is the secret key, and the output of this sign function is your signature. So whenever you change your message, the corresponding output signature, it also changes. That means the generated signature, it in turn depends upon the signature, or it depends upon the document that you are signing. Okay, so if you produce another document, okay, so your signature would vary according to this sign function. So the sign method outputs a signature seek for message under the secret key SK. And then the verifier, what does he do? He takes in that signature, okay, and then he verifies with the public key that whether the message is indeed correct or not. So it returns a Boolean value is valid. So, okay, so this can be either true or false. So that will be true if the signature is a valid signature for this message under the public key PK. Otherwise, it detects that the signature is a false signature. Somebody else has given the signature. So in this, the generate keys function and the sign function, these are randomized function. Okay, these are randomized algorithms. Okay, so the generate keys when randomized generates different keys for different persons. That means it's depending upon the person. Means a person comes at 3 p.m. he would get a different set of SKPK. A person who comes at 4 p.m. is who invokes this function at 4 p.m. in the afternoon, he would get another pair. So that's why it is called randomized. The generate is a randomized algorithm. It generates different keys for different persons, and it shall verify and inject and verify function. This is a deterministic function. The security properties: valid signatures must verify. Okay, if a message if the same message has to be verified, if the same message is verified, then the output of verify must be true. The signatures are existentially unforgeable. Okay, existentially unforgeable means once you have signed on a particular message, your signature should not be forged by any other malicious user. Okay, so an adversary who knows PK gets to see signatures on the messages of his choice. Okay, but he cannot produce a verifiable signature on another message. Okay, so what an attacker can do is that an attacker also knows the public key of the owner. Okay, so as an attacker, he also knows the public key of the owner. So even though he knows the public key, he can what he can do is that he can give multiple documents to the owner. The owner signs it back. Okay, that means now the attacker has a set of the documents along with the signatures that are provided to him. So even though if he has performed n number of queries, he is unable to forge the signature. That means he cannot produce a verifiable signature on another message. So this is what is being said to be the unforgeability game. So what this represents is that this challenger, say suppose challenger is the one who signs the document. That means he is in possession of the secret key and the public key, and this public key is known to everybody. So this public key is known to both the challenger. Challenger means the owner. Okay, and this public key is available to an attacker as well. So what does the attacker do? He gives it he sends the first document, that is M0, or the first message M0 to the challenger. As the challenger has a secret key, he uses this secret key to sign the document. Okay, so he uses that secret key to sign the document. He sends the corresponding signature. Okay, so now the attacker has a signature corresponding to the document M0. Then he again sends another document M1. He obtains the corresponding signature on that document. Okay, so likewise, suppose he performs n number of queries. Okay, he gives n documents and he obtains the signatures on all the n documents. So now he has in possession n number of documents and their corresponding signatures. Now with this knowledge, what does he do? With this knowledge, he creates a different message M and a signature value SIG. Okay, and he passes on this different message value or a different document and the corresponding signature to the challenger. What does the challenger or the owner do? He verifies. Okay, he verifies that whether this signature is indeed that of this new document. If this signature is indeed that of the new document, that means this attacker is successfully able to forge the challenger, the signature of the challenger. Okay, so if this verify is true means this SIG, this attacker has generated a true signature of a new document. That means this in all the previous queries, the signature was generated by the challenger. But now, in this new query, this attacker is able to forge the challenger signature corresponding to this document. Okay, so if the challenger indeed verifies that indeed this thing is a signature, is a valid signature of this document, then the attacker wins. So this is called the unforgeability game. So in the security notion, it is being said that the probability of this verify function to return the value true should be infinitesimally small, should be negligibly small. Okay. So that's when you say that this game, that this digital signature satisfies the unforgeability property. So in the real world scenario, the algorithms are randomized. As I said, the generate keys and the computation of the signature, they are randomized. So for that, you need to have a good source of randomness, and it puts a limit on a message size. So there is a limit on the message size that you can sign. Okay. So what happens is that as this computation has to be done, that is computation of a hash function is done on on in in a limited amount of time. What you do is that if the message size is very large, what do? You create a hash of that message size, and then you sign the hash of that message size. Okay, instead of signing that entire large message, what do? You sign the hash of that message. Okay, so there is a limit on the message size for timing restrictions, due to the timing restrictions. So to increase message size, assign hash message rather than the message itself. Okay, and that hash should be collision resistant to fix this issue. So this is an information that in a blockchain, whenever you are signing a record, you are actually signing the entire set of the records that exist within the system. That means you are authorizing that no, not only my record, all the previous records are secured. Okay, so a signature covers the whole structure of the blockchain. That means you are authorizing the entire record over here. So in Bitcoin, it uses the elliptic curve digital signature algorithm. So I'm not going into the mathematics of this elliptic curve digital signature algorithm. It comprises a whole lot of algebraic theory in this, algebraic structures in this, or abstract algebra. Okay, but the bottom line is that the good randomness is extremely essential. Okay, for instance, in the generate case, and in the sign function, this randomness is absolutely necessary. Even though you are not able to generate a true random number, the random should that number should be a pseudo random number. Okay, and if there is any sacrifice or any compromise in generating this randomness, then your secret key can be leaked out and the game would be open. Okay, so any attacker in that case would be able to get your secret key in that case. So that's why you need to have a good source of randomness for these two functions. So this elliptic curve digital signature algorithm, it is a US government standard, and it is proven to be cryptographically secure. Okay, so this standard elliptic curve used is SecP 256K1. So this is the standard elliptic curve that is used in this digital signature algorithm. So it has a private key, as I said that a signature should have a private key as well as a public key. The private key is of 256 bit, public key is of private key is of 256 bit, public key is of 512 bit, and the message to be signed is of 256 bit. So if the original message is a very large file, say a video file, so what you can do is that you can create a hash of that video file, and that hash is say you pass that video file through a SHA function, SHA-256, the output of 256, SHA-256, the 256 bit output, and that is treated as a message to be signed, and the signature is a 512 bit output. So the ECDCA can only sign 256 bit long messages. So this is one of the restrictions of ECDCA. So you need to parse. So you need to split the messages into 256 bit data each. Okay, so this is used as a public. So this identity of a person in the system is often used as a public key in the digital signature algorithms. Okay, so you create a new identity using the generate keys every time you invoke that function. So here is an example of a Goopy coin currency that I will come to. So this will conclude the talk. Okay, so this Goopy coin is an instance of a cryptocurrency which shows you that how the cryptographic primitives are used in any cryptocurrency. So over here, Goopy is a person who can create new coins, and he can send those coins to the market. Okay, so Goopy can create new coins whenever he wants, and these newly created coins belong to him initially. Okay, and he can give away these coins. Okay, for instance, in the previous lecture, Dr. Nivinas showed you that a note represents the bearer. Okay, so bearer claims that anybody who has a particular, say, a 1,000 order or a 2,000 rupee note, he can claim 2,000 rupees. So here Goopy is that bearer. Okay, so Gopi is the authorizing agent. Okay, so Gopi can create new coins whenever he wants, and the newly created coins belong to him. So whoever owns the coin, okay, only he can transfer it to somebody else. Whoever else, okay, if a Gopi gives a coin to me, okay, only I should be able to give that coin to somebody else and nobody else. That means that coin cannot be spoofed. That means a copy of that coin cannot be produced. Okay, so this is being ensured by this hash function of a blockchain system. So how to create a coin? So we'll see how Goopy creates the coin to ensure this thing. So Goopy creates a new unique coin ID with a unique coin ID that he has never generated before. So this unique coin ID is a randomly generated ID. Okay, and what does he do? He puts this unique coin ID to a function and he constructs this string. Okay, create coin unique ID, unique coin ID. He signs this string, this generated string. What does Goopy do? He has first created this string and then signs this string, which is secret key. He appends the corresponding signature along with that string to create the coin. So the coin comprises of this string and the signature of this string. Okay, so this signature is being generated by the secret key of Goopy. So this is so these are the two components of the coin that Goopy has created. So anybody can verify that the coin contains Goopy's valid signature. Okay, so signature is being generated from the secret key of Goopy. So anybody who wants to validate the signature, he uses the public key of Goopy. Okay, so anybody can use the public key of Goopy to validate that indeed the coin started from Goopy. That means Goopy was the original owner of this of this coin. So rule 2. Transferring a coin is done through a set of cryptographic operations. Okay, so when a coin is being transferred from person 1 to person 2, it is being done through a set of cryptographic operations. Okay, so as to ensure the property that coin is not copied. Okay, so suppose Goopy wants to transfer this coin to Alice. Okay, Alice is a user in the system, and Goopy was the sole agent. Okay, so Goopy was one of the agents, so he wants to transfer a coin to Alice. So what does he do? Goopy creates a statement: pay this to Alice. Okay, that means pay this coin. Okay, so this string means pay this coin to Alice. So this is said pay this to Alice, wherein Alice is basically the public key of Alice, and this is basically a hash pointer. Okay, so this is a hash pointer that references the coin in the question. Okay, so this means this is a hash pointer that points to that coin. Okay, so the coin that Goopy has generated, he instructs that this coin should be given to Alice, where this Alice is basically the public key of that person, Alice, with name Alice. So Alice is basically Alice's public key. Goopy signs this entire string. Okay, since Goopy originally owned the coin, he has to sign any transaction that spends the coin. Okay, so whenever a coin changes the hand, okay, whenever a coin travels from person 1 to person 2, Goopy always has to sign that statement. Okay, to keep a note that to keep a trail to which set of persons did the coin travel. Okay, and as Goopy was the originator of the coin, he always has to sign each and every transaction. So Goopy signs the strings representing that statement. Since Goopy originally owned the coin, he has to sign any transaction that spends the coin. So once this data structure representing Goopy's transaction signed by him exists, okay, so whenever Goopy signs this transaction, then that coin, then Alice owns that coin. So after Goopy's signature for that transaction, that coin is transferred to Alice. Okay, so now Alice has that string along with that signature. So now Alice can prove to anyone that she owns the coin. Okay, so at any point of time, okay, as long as she has the coin, she can prove to anybody that she owns the coin. Okay, she can present the data structure with Goopy's valid signature. Okay, she can show that okay, this is the coin and this is the valid signature. Okay, so anybody else cannot copy that signature because that signature is tied to that coin only. Okay, so now Alice. Now suppose Alice wants to buy an item from a market from a person named Bob. So when Alice buys an item from Bob, she pays that cryptocurrency to Bob. So what does she do? Alice creates a statement. Pay this coin to Bob's public key. Okay, so over here also, this is a hash pointer to the coin, and she instructs that this coin should be paid to the Bob's public key, because Bob's public key is basically the identity of Bob. So this is a hash pointer to the coin owned by Alice. Alice signs this statement. Alice then signs this statement. Okay, because Alice is transferring that coin. Anyone, when presented with this coin, can verify that Bob is the owner. Okay, so now after Alice signs this statement, and of course Goofy also signs at his end. Okay, to keep a record. So anyone presented with this coin can verify that Bob is the owner, because Bob has the valid signature now. So all verifiers follow the chain of the hash pointers back to the coin's creation. Okay, so any verifier, he has to verify the coin. He needs to verify until the point of coin's creation. So verify at each step, the rightful owner signs a statement and that says pay this coin to new owner. So whenever a person wants to give that coin to a person 2, he says pay this coin to the public key of person 2. Okay, so this new owner is basically the public key of person 2. So this is the diagram. Okay, so signed by Goofy. So first this coin is being created by Goofy. It is being signed by Goofy. Okay, and then it traverses it, and then Goofy gives it to Alice. So pay to public key of Alice. So now at this point the coin is with Alice, and then when Alice buys an item from Bob, then this record is being created. Pay to Bob. Okay, and it is being signed by Alice. Okay, so this is created at the bottom and then spent twice. So this is an instance of a cryptocurrency transaction. Okay, so over here the hash function is used in a digital signature. So the rules of a Goofy coin transaction: Goofy coin can create new coins by simply signing the statement that he is making a new coin with a new coin ID. Whoever owns the coin can pass it to somebody else by signing a statement and saying pass this coin to the public key of the person 2. X is specified as the public key. So anybody can verify the validity of a coin, okay, because he can pass that coin through their signature by following the chain of hash pointers back to the creation by Goofy. Verify all the signatures along the way. Okay, so all the signatures across the chain of transactions could be verified. That case. Okay, so this is where I end my talk, wherein we demonstrated, where we saw that how the cryptographic primitives are used in a typical cryptocurrency. Thank you. So any questions you have? So is cryptocurrency legal in India? So this is the question. At this point, the government does not authorize any cryptographic transactions over here. But indeed, you can use blockchain for any system. This blockchain is being used for keeping land records. You can use for keeping records of any transactions. Okay, but cryptocurrency it is still not used, because it basically removes the role of any central agent. So that's why cryptocurrency is presently not legal in India. Anybody else have any questions?
Anyone have any queries?
Blockchain can be used. Yeah, indeed, blockchain can be used.
If you have any questions, please check on the chat box. Write on the chat box.
Okay, so there is a question by Rajni Mohana. The question is.
Yes, sir. There are some questions in the chat box.
Yeah, I can see. So this question is from Rajni Mohana. She is asking that can blockchain be used in the healthcare domain? Yeah, indeed, blockchains can be used in a healthcare domain, wherein patient's health parameters. Suppose a patient needs to undergo a series of tests, say a blood test or any say the MRI test, and so on and so forth. So all these records can be kept in the blockchain system, and any doctor and a doctor who wants to see that record, he needs to have a proper set of keys to go through that record to see the corresponding records, to see the corresponding test reports of that patient. So indeed, blockchain can also be used in the healthcare domain. So any transaction you can think of wherein it depends between two or more persons, and any such transaction can be kept as a record using the blockchain. But you need to ensure that how that records are being kept secure. If, for instance, I saw that the probability of guessing a sample within a sample space should be negligibly small. So all these properties need to be ensured when you are implementing a blockchain system. That C2 randomness property should be there. Any other questions? Do you have any other queries? So thank you everyone.
Thank you, sir.
Okay, thank you.
Thank you, sir. Thank you. You can share with your fabulous knowledge in the form of your cryptography and the various property. And thank you for all those are attending this FDP. I hope all are getting the important knowledge by Dr. Bodhisatwa Mazumdar, sir. Thank you, sir. Thank you for all. Hello. Hello. Okay. Feedback form is available in the chat box. In your group, FDP, WhatsApp FDP group. So please check this.